Hello, everyone, and thank you for joining us today on this webcast on implementing MLOps. My name is Archana, and I'm joined by my colleague Brendan. We're both business intelligence and analytics consultants at Thorogood, and we're joining you today from Philadelphia. If you have any questions on the content covered today or more broadly about data analytics and AI, feel free to get in touch via email or LinkedIn. As always with our webcast, we'll kick off with a very brief introduction to Thorogood. We'll then introduce the concept of MLOps and the benefits it brings to the business. We'll spend the bulk of the session sharing our thoughts on the key design considerations that we believe are essential to keep in mind when implementing an MLOps framework. So first off, who are we? Thorogood is an independent and specialist business intelligence and analytics company with a focus on data engineering, data science, and data visualization. Our approach is rooted in understanding business goals and using the capabilities of technology to meet these goals. So customers and business objectives are at the forefront of our approach. We are a global company with offices and consultants in Asia, Europe, and the Americas. We offer a full range of services when it comes to data and analytics. So right from data and technology strategies and roadmaps, end-to-end implementations of data and AI solutions, user empowerment, and analytics, AI, and ML services. Our customers are typically multinational blue chip organizations and have a few of them listed on the screen. Whilst not limited to these four verticals, many of our clients do fall into one of these four very data-rich verticals. So consumer goods, pharma and life sciences, financial services, and insurance. Some of you may be familiar with this already. We are running an MLOps webcast series. The first installment was held last week. My colleagues Emily and Sarah shared their thoughts on the business case for MLOps. Essentially, why should organizations care about MLOps and what's the value that it brings to the table? Today's session is obviously focused on implementing MLOps, and the third and final session will focus on the adoption and rollout. Before we get into the depths of MLOps, let's go through some basic definitions. DevOps is pretty ubiquitous now, and its implementations are pretty mature in most organizations. DevOps is a set of practices and tools that combine software development and IT operations and aims to streamline the software development and delivery lifecycle. DevOps addresses the constant need for responsiveness and enables teams and processes to be more efficient and reliable. All of this really leading to a rapid pace of innovation and growth. Moving on to machine learning operations, or MLOps. This refers to practices for orchestrating the industrialization, deployment, and maintenance of machine learning models in a scalable and standardized way. There are a number of similarities between these two practices, but also some pretty big important differences that particularly influence some of the design considerations that we're going to touch upon today. Let's now look at what a machine learning operations lifecycle looks like. It's obviously important to understand this before implementing a framework to appropriately support these activities. So we start with the define phase, where you understand your business needs, define your hypotheses, and identify the data sets that you work with. You then move on to the experiment phase, where your data scientist iteratively builds your model until it achieves desired results. So this will typically start with cleansing and wrangling your data to get it to the right format. You then select the key features that will drive your model or algorithm, and then train, evaluate your model with the various data inputs, features, and parameters. Obviously, this isn't a one-time process, and you'll need to go through this multiple times until you get the desired predictions in terms of accuracy and quality, and you have a model that's ready for productionizing, which takes us into the next phase, which is industrialization. So you productionize all of your pipelines and components that are needed for the model to run at scale, and build in automated testing and monitoring processes as well. The last piece of the puzzle here is the monitor and improve activities. One of the biggest differences between MLOps and DevOps is the changing data inputs does affect the model outputs, and therefore continuous monitoring and identification of opportunities to improve performance or quality becomes a very integral part of the MLOps lifecycle. As I mentioned, the first webcast in this MLOps series focused on the business case for MLOps and its myriad benefits, including empowering data scientists, quicker time to value, and increased trust and accuracy of the model predictions. I won't go into more detail here, and feel free to watch the recorded session that's up on our website or YouTube. But for now, let's pivot to the main topic for today's session around implementing an MLOps framework. So we've defined four main pillars that form the backbone of a successful MLOps framework. Start with people. So what skills does your team need? How many people do you need? What roles do they play? Processes. So how do you keep an MLOps implementation going? What are the processes that are needed to move from the ad hoc experiments run by data scientists to productionizing their models? What tools should you use? What is the optimal technical design? There's obviously data that underpins everything you do with machine learning. Today, we're going to focus on the tools and the technical design considerations that come alongside this in implementing a framework. We're going to look at this from two perspectives. First, what are the fundamental and baseline features that support the successful operationalization of ML models? Secondly, we'd also like to share with you some other considerations that we've observed and learned while defining and implementing such frameworks with our customers. I'm going to talk about 6 key considerations today that are valuable to keep in mind. Obviously, this isn't an exhaustive list, but these are just the 6 important topics that we thought would be useful for this session. I'm going to quickly bring up the topics, but we'll get into each of them in a bit more detail. Tool selection, code management, automation, parallelization, inferencing approach, and model monitoring and metrics. First off, tool selection. There is a plethora of tools available to support the end-to-end machine learning lifecycle. A few of the major players in the market are Microsoft's Azure ML, GCP's Google Cloud ML, Amazon SageMaker, and Databricks. Databricks, of course, can integrate with each of these 3 major cloud platforms. An MLOps framework or platform can be implemented across many different technology stacks, but selecting the right one for your organization and team is critical to realizing the full value and potential of ML experiments. So which one is the best fit for you? I should also say that it needn't just be one tool, and it's fairly likely you may have multiple tools available within your strategic landscape. And just like all tool selection decision, you'll want to think about how an ML tool would fit in with the rest of your landscape. So the integration and cohesiveness it offers from a model development, training, deployment, and monitoring perspective. Another aspect to consider are the skills your data scientists bring to the table and the learning curve that might be involved in getting them to adopt potentially a new machine learning tool. Bear in mind that tool selection is also not just a one-off exercise, and particularly when you have multiple tools within your landscape, this decision does need to be made for every ML use case that is onboarded. And this choice of technology may be dependent on how many models are being developed, the scale of the solution, the training and inferencing requirements in each case. I'm now going to jump to code management, which is one of those features that is common to both DevOps and MLOps. The value of code management is pretty well established at this point. The obvious benefit is that with a central code repository, you have a single source of truth that can be used as the basis for ongoing development and enhancements. With versioning, you'll also have access to older versions of code, irrespective of whether they worked or not. Code management can play a crucial role in ML projects as model versioning is important to track and can very quickly grow. Now, the importance of having a code management strategy in place, or perhaps lack thereof, can be painfully evident when multiple people are working on improvements to the same piece of code, only to have one set of changes overwritten. In the context of an MLOps project, where you may have a team of data scientists and data engineers collaborating on the same underlying code base, a single source of truth with versioning and auditing is a must-have. I'd like to quickly walk you through what a branching strategy may look like for an MLOps project. And the reason I do this is because adhering to a branching strategy can help the team collaborate better and spend less time managing version control and more time developing, quality code. We found that a 3-branch strategy to be very useful. So the main branch should be the current version of the code and built cleanly without error. The feature branch is where new features should be added and bugs are resolved. It's isolated from the main branch and gets integrated only when committed. Development in this way also enables auditability, especially when you're looking to resolve any issue that comes up. The final branch is the release branch, which is a snapshot of the main branch that gets deployed to your environment. The release branch in this visual is a snapshot of version C, which may be an updated version of an ML model that you're deploying for consumption by your business users. Let's say you then have to update the algorithm to account for a new feature or update the parameters of your model. A new version E will then be needed to overwrite the previous version that was live. Well, this is just a sample of a branching strategy. The overarching message is that the central code repository with very clear definition of ways of working with source control is imperative for a smooth running MLOps implementation. Automation is pivotal to realizing the benefits of MLOps. So let's look at a few areas where automation can be implemented into the framework. Continuous integration and continuous delivery is a key tenet of DevOps that's equally applicable and relevant to MLOps. Using CI/CD pipelines, we can build processes to build or deploy code at the click of a button, or better yet, it's fully automated. New models or changes to existing models can be easily deployed through reliable processes that always execute the same set of steps. You may want to take that a step further and build in automated tests within these pipelines. On the continuous delivery side, these pipelines should be set up so you can promptly deliver models to business users for consumption, accelerating time to value and insights. Automated processes are not just applicable for the productionized versions of the models, but should also be built to support the initial experimentation phases, thereby enabling data scientists to quickly go through iterations of the model. In some use cases, your model may need to be set up to generate predictions on a set cadence based on when your data may be available. So let's say you receive weekly sales data on your model predictions. Weekly sales data and your model predictions need to be refreshed on that schedule. So setting up an automated trigger removes any manual process and ensures that reliable and up-to-date predictions are always available. Brendan's going to share some thoughts on the need for monitoring in just a few moments, but one big difference in MLOps as compared to DevOps is continuous training. This really relates to identifying scenarios that require a model to be trained and redeployed to production due to a performance degradation in the current version of the model that's been deployed. And this capability of continuous training must be built into the design of any MLOps framework to ensure that you're always providing accurate outputs despite potentially changing inputs. All of these pieces work in unison to bring about efficiency, but also give time and value back to your data scientists. So they can now focus on building more models and answering business problems instead of focusing on the process elements of an ML life cycle. One final point here, in conjunction with automation, parameterization plays an important role in designing effective and efficient solutions. So much like a MATLAB lets a user enter in their own words to story, parameterization does the same with code. In machine learning, we see this playing a role in allowing a single model to be used and to be reused and generate varied outputs. So let's say a model needs to be run for different products. Instead of building individual copies, you can put a placeholder in for the product dimension and allow your user to specify the value for that product when you execute the model, thereby building a dynamic solution. Parameterization should also be used when building pipelines. So you can use these parameters to toggle the values of your target environments. So that's a peek into some of the fundamental features of MLOps. I'll now hand over to Brendan, who'll share his thoughts on some of the nuances specific to MLOps based on our customer experience.
So yeah, as Arshna mentioned, I'm just going to walk through some of the more technical considerations and how it relates to a typical ML lifecycle as a whole. The primary objective of any MLOps framework is to productionize analytics to easily distribute and consume models at scale. And to do so requires thinking critically as to how to take a model from local experiment to parallelized solution. And that leap is where MLOps, as the true value of an ML model, will truly be realized when it can scale to perform when ingesting the large volumes of data that will ultimately inform key business decisions. And with any MLOps project, a key tenet is to ensure that if refactoring model code for scale is needed, an MLOps engineer that is driving the refactoring and parallelization process doesn't compromise on that existing model act. And why I lead with this is the priorities of the data scientists that are developing these models, which although are aligned with the idea of productionizing and scalable analytics, may differ slightly in some cases, which could make refactoring a challenge. We've sometimes seen that a data scientist will prioritize the accuracy of a model and its outputs over the ability to scale. And that's not to say performant and scalable code isn't considered, but the accuracy of the model will certainly take precedence. In some of our implementation work, we've come alongside some very powerful and effective models. But it does require the expertise of an MLOps engineer to help assess and refactor the code for scale and performance. With an appropriate MLOps framework and a team, sort of positioned and situated to support the data scientists' existing experimentation, the models will retain their accuracy and will continue to provide that business value. And when dealing with large data volumes, as many ML applications do, it's important to be able to manage costs from both a monetary and a time perspective. Parallelizing the data engineering, training, and output generation is a prime way to do just that. Parallelizing is a form of refactoring and could come in the form of a variety of ways, most notably when MLOps engineers will need to work on models that rely on using Pandas-specific data formats, which is a Python library well known for its inherent data analysis capability. But where Pandas falls short is that it struggles to handle large volumes of data. By nature, Pandas is limited to processing a single node within a cluster. Because of this, the processing of a Pandas data frame can't be distributed and parallelized, and obviously this presents a significant issue from a scale perspective. However, there are approaches like Parallel Run Step in Azure ML or Pandas UDS and Spark that allow you to batch out the training of models across nodes. Being that Pandas is so widely used amongst data scientists for its synergy with powerful ML libraries, it's important to understand two possible ways to parallelize and appropriately scale solutions we at Thorogood have considered when coming alongside our clients. Rather than moving away from a tuned or accurate model that uses these Pandas-specific data frames as inputs, there are Pandas UDFs, or user-defined functions that can be used to scale your experiment. At a very high level, these work by defining and transforming your initial data set as a Spark data frame as opposed to a Pandas data frame. Because remember, those Pandas-based workloads can't be distributed across nodes. The Spark data frame functions as your input for your Pandas UDF and is partitioned into smaller and more manageable Pandas data frames that can be spliced by the characteristic of your choosing, like specific products, brands, or even characteristics. This method of Pandas UDFs ultimately couples the parallelized flexibility and power of Spark while still retaining the manipulation properties of your Pandas-based model. Another approach, but one that takes significantly more effort, is to refactor your existing model code to PySpark to unlock the cluster computing capabilities. The advantage with this is that with PySpark is that it's best for distributed processing across nodes, which will in turn enable mass parallelized processing that's obviously very conducive when dealing with the massive data sets required for sustainable ML. As the applications of ML have grown more broadly too, more and more Spark native libraries, or more and more Spark ML native libraries have developed, perhaps most notably in MLlib, that could potentially serve as go-tos for analysis, training, and modeling of massive data sets in the future. Refactoring an entire model is certainly not a walk in the park, but refactoring code to Spark should really only be considered when the data required for modeling can't fit on a single node, as Pandas-based models will still be able to perform better than PySpark-based ones in this particular instance. Another key consideration is an organization's inferencing approach. So how can you serve your model predictions and how can they expect it? How are these model predictions expected to be used downstream? And there are primarily two methods. The first will be when a machine learning model has been built to serve a use case where predictions need to be generated as soon as the latest data is available. So let's say you have sales data that comes in on a monthly cadence and you need to refresh your model to reflect the latest month's trends. In this case, you may want to generate predictions and store it in some data mart for where it can then be consumed by other applications or even directly by users. This first scenario is called batch inferencing. Alternatively, the predictions from the model may need to be consumed on demand directly by your end users. So this may work on the latest data that's available at the time, or perhaps it's even driven by some parameters. So of course, the tools you use to deploy and serve your models vary based on what path you choose. So in addition to that, I just want to highlight a couple of additional considerations. With the batch inferencing approach, you do need to factor in that your demand and load levels are lower, and you can appropriately size your compute clusters based off of that. So it's also a good opportunity to include parallelization in your ML pipelines for further optimization. So with real-time inferencing, on the other hand, the ability to scale and handle a high volume of requests is the top consideration when designing or serving architecture. Realistically, any MLOps framework for an organization is likely to have to support both inferencing methods, so both batch and real-time. But there's definitely a case for a decision to be made on a model-by-model basis to really pick the inferencing approach that's best suited for the model and the business users. And this obviously will have some cost implications as well. For all considerations that need to be taken into account when technically implementing an MLOps solution, it's just as important to ensure that your productionized ML model is still generating healthy and quality predictive outputs. The way in which we can ensure that the model is still generating consistent quality outputs is to monitor the technical performance and the model quality in an automated fashion. This is obviously a key and significant step in the overall flow of an ML project lifecycle. So technical performance metrics monitor the more technical nature and health of the model and how performant it is. Metadata like compute cost, latency, and input parameters can indicate whether a model is performing as expected. These metrics should be, automatically written out alongside your model outputs in the form of some logs or, other structured outputs to confirm that the model is still technically healthy as expected. And writing out these metrics will also enable, a comprehensive auditing of your model version history. So as new improvements and features are added to a model over time, there's a paper trail to inform how the model is expected to operate compared to previous versions. Model quality metrics, on the other hand, measure the actual predictive quality and accuracy of a model that looks to evaluate things like loss and overall precision to quantify whether changes need to be made to how a model is formulating predictions. Automating these checks to detect the deterioration of predictive outputs is a key step in the automated productionized framework an MLOPS solution provides. Monitoring model metrics, including those that indicate drift, something that that we are acutely aware of within our ML models. Are key to ensuring and maximizing the accuracy of predictions. Data obviously changes over time, so having an ML model that can automatically be trained and retrained on the latest data available will allow the model to retain the high predictive quality that we expect it to. But what is drift and how can we look to monitor it? So there are really two kinds that we look to monitor for when generating model outputs, both contributing to model decay. First type is concept drifts, which can be described as the changing relationship between inputs and outputs of our models. Basically, the historical data that our model has been trained on is not as relevant as it once was through a change in the meaning of what we're trying to predict. In a perfectly static world where there are no external influencers on our model, concept drift wouldn't exist. But in a world where industries are changing so rapidly and dynamically, it's not hard to see how a model may degrade in its performance if an emerging or unanticipated trend, became a force within the market. An example to tangibly think about concept drift, and as a clear example of an unanticipated external factor, is the emergence of COVID a year and a half ago. So let's just think about how in January 2020, companies that manufactured hand sanitizers were able to forecast their sales for the entire year and plan out the actual manufacturing of their product and the shipping out to various customers for all of 2020 based off historical demand. When March of 2020 rolls around, those predictions and the models that generated them we're certainly not anticipating the mass purchasing of hand sanitizers across shelves throughout the world. And surely, this is an external factor that you can't really anticipate. And although it's pretty extreme, the same thing could happen with less prominent external factors that could still lead to significant disruption. But with an appropriately tuned, automated monitoring solution as part of an MLOps framework, this concept drift can be detected and handled accordingly. It's also important to call out data drift, which instead describes the change in the underlying distribution and overall meaning of new data. To think about how this is different is to take a common example of identifying fraud and from spammers in some sort of messaging application. So we'll say that our model was trained on identifying spammers, and throughout development, the application had the actual messaging application had a limit on the amount of messages its users could send in a given minute. Say we'll cap it at 10. The model was really good at identifying spammers and found that most users that were messaging more than 5 times per minute were in fact spammers. But out comes a new software update that raises this 10 messages per minute cap to 100. And now with this new update, spammers and normal users alike are now messaging a lot more. So the change means that our model, because everyone's messaging a lot more now, is classifying our spammers and normal users as one and the same as all spammers. Obviously, this isn't the case, but due to a shift in the distribution of data, that the model was trained on, it was making some mistakes. So I guess in summary, concept drift explains the shift in relationships between variables, and data shift explains the shift in data distributions. It's a small difference, I suppose, but we need to be able to monitor when our models are degrading so that we can catch these issues and retrain and or refactor our models accordingly. We've now kind of discussed some of the key features to enable operationalization and some of the technical considerations to facilitate the implementation of an MLOps framework, but what does this actually look like? So we'll briefly take a look at a sample architecture of an Azure-based stack that does support MLOps. And to begin, we have data engineering. So we have Data Factory in place for our data ingestion, and in conjunction with Databricks is in place to transform our raw data as required to flow to our data lake, and parallelly our data mart that supports our end user applications. We then introduce Azure ML, which is for experimenting and developing models. But with this framework, we're also keeping in mind, within Azure ML, we're keeping in mind some of the more technical best practices for development, like thinking about scale and obviously cost considerations that are ultimately going to help the productionization of these sorts of experiments in the context of an MLOps framework in the future. Then there are really two ways we can serve the models, as we discussed earlier. Batch inferencing via designed AML pipelines or AML managed Kubernetes services for a more real-time approach. And obviously, as we're serving our models and generating them, we always want to be monitoring our model's performance to ensure everything is behaving as expected and isn't subject to things like drift or other quality issues. And lastly, all of our code, whether it be the data engineering, the model development, or the infrastructure setup, should all be managed using some sound DevOps principles. In this case, we're using Azure DevOps. But now I'd just like to introduce how Thorogood can help implement these types of frameworks for you and your organization. We do have experiments in strategizing and implementing MLOPS frameworks at the organizational level. And I think from a more assessment level perspective, it's really important to understand where an organization and all of its ML applications and experiments stand from a maturity perspective. And after this evaluation and self-reflection, it makes sense to subsequently strategize next steps and implement some of the more technical aspects that we've discussed in this webinar. And if you're interested in learning more as to how Thorogood can help implement an MLOPS framework in your organization, do reach out to Archana and I, as we'd be happy to discuss more with you. Additionally, a few consultants from Thorogood recently presented a session at Databricks' Data and AI Summit last month. And this session was based on our learnings from developing MLOps strategies for enterprise customers, specifically focused on some learnings from a CPG engagement where we tested a framework by implementing MLOps industrialization principles and ongoing monitoring and support of existing models. So if you're interested in this session as well, again, it is available on Data and AI Summit's website. But if you would like more information about this particular engagement or our learnings, do feel free to reach out as well. I'd be happy to discuss with you. And lastly, as Archana alluded to earlier, this is the second part in our MLOps webinar series. And we do have our final and third installment in a couple weeks from now on July 8th, which deals with managing the successful adoption of MLOps and sort of how you can work to make sure things sort of stick within your organization. So that being said, we also have some other material on our website as well if you're interested in learning more about some of our other experiences within this field. So again, I'd like to thank you all for joining. And again, please feel free to reach out to Archana and I if you have any additional questions. Thank you.